All right, so let's do a few practice problems um, finding the derivatives of functions involving trig functions. So let's take a look right here. We're looking for f prime of x for f of x given 3 cos x minus 5 tan x plus 3. Again, we have that rule of differentiation that it's a linear operator, meaning it can be split over sums and scalar multiplication. So I'm really taking the derivative of this plus the derivative of this plus the derivative of this. And so the derivative of 3 cosine is 3 times the derivative of cosine, which is negative 3 times sine of x, right? Why? Because the derivative of cosine equals negative sine x. So that we use here. Tangent x, right? The derivative of tangent we said was secant squared, right? So this becomes negative 5 secant squared x because of that proof we did above. And then what's the derivative of 3? It's 0, right? Because that's just a constant function. So we have this is our derivative for this function. All done. Yes, it's that simple for this one, right? Because that was just a sum. But we have other rules. We have other ways we can combine these things, right? It's not usually just sums of trig functions. There's products. There's all sorts of different combinations. So if I'm looking for g prime of w, the instructions here are to find all the derivatives, by the way. So here, finding g prime of w, what is the function that describes this rate of change? Well, we're going to, need to take the derivative of this product of two functions. Hint, hint. So how do we deal with that? We use the product rule. Or if you want to call this f, call this g, that's fine. Or you can use, this method of setting up brackets to kind of deal with it ahead of time. Whatever works for you in terms of the bookkeeping. So, we have what f prime g plus f g prime. And so we know the derivative of both of these functions based on what we did before. Derivative of tangent is secant squared w. We know g is just secant w. F is tan w. And the derivative of secant w is secant w tan w, right? From what we found before. So now we can do a little bit of simplifying here. Secant squared and secant is just really secant cubed w plus secant w times tangent squared w. This is the level of simplification I'd expect. You can probably go a little bit further with this. There might be a Pythagorean identity, things like this. But really, I ask for just a reasonable amount of simplification. So that's obviously a gray area, but to not leave it like this where you have two factors that could be combined into a single term, with an easy step like that. But here we have g prime of w based solely on the rules that we know so far. All right. Let's take another peek here. This function doesn't have a name. Let's call it p of t. And we want to find p prime of t. Well, here I have a sum of two terms. Again, differentiation splits over those. I know my first term will be 3t squared. And then my second term here, minus t squared sine t, this is a product of two functions, right? This is a product of a power function and sine function. So again, I will want to set myself up with a product rule, and I will go ahead and take these derivatives. So f prime is negative 2t times sine t plus negative t squared times cos t, derivative of the second function. Okay. You'll notice how I dealt with this minus sign. This is one way to do it. The other would have been to maybe do 3t squared minus and then have this whole thing be negated and just deal with t squared sine t prime, but you need to remember that this is all in brackets and being subtracted. Here I just said I'm going to take the addition of these terms and then I carried the negative through it. It works out the same, but you really got to be mindful of the negative sign, is all I'll say. All right, so let's see what we can simplify here. Not much. We can just drop some of these brackets to make it look a little cleaner. So 3t minus 2t sine t minus t squared cos t. This is my derivative here. Again, what does this derivative do? It describes the instantaneous rate of change of this function. It gives you the slope of the tangent line. And here's another one. Again, involves a quotient. We don't have access to the chain rule yet, so we will use the quotient rule here. So f prime of t will be the derivative, right? We want fg prime, or f prime g, sorry, minus fg prime all over g squared. F prime is 0, that first term being 0, minus fg prime. Well, let's go ahead and find out what g prime should be. If this is g prime is 2 cos t plus 3 sine t, knowing these two derivatives here, right? So minus fg prime, that's minus 1 times g prime. So we're just negating what we have up here, which is really negative 2 cos t minus 3 sine t all over g squared, 2 sine t minus 3 cos t squared. And we can leave it like this. This is fine. Again, if you're using online things to check your work, they might suggest a lot more simplification. This is not necessary for me, and honestly, that can just get you confused and lost. So this is a good way to go. So that's a few derivative problems with a few of the rules that we've seen so far. You'll obviously have more and different combinations in your homework, so we can't cover all possible permutations of this, but it seems like we've got a good footing for you to go off and practice on your own at this point. And one last kind of applied problem I wanted to cover here was finding the equation of a tangent line. You've done this a bunch, and so I wanted to go over it here in this context as well. To find the equation of the tangent line, or what we often call the line of best approximation. English is hard. Right, it's the line that approximates the function the best at a point because it has the slope of the tangent line. It's behaving exactly like the function is in a local neighborhood for this function at t equals pi over 4. So what do you need for the tangent line? Excuse me. The equation of the tangent line is what? Y minus f of a equals f prime of a times x minus a. This is it in point slope form. Well, here our a is pi over 4, and our f is this g of t. So we could, I mean, maybe we don't need to be so tied to our initial notation. We can adapt it for here. So y minus g of a equals g prime of a, slope of the tangent line, times x minus a. So we can even be more specific. Y minus g of pi over 4 equals g prime of pi over 4 times x minus pi over 4. And here our x is what? T. So this is what we're on the lookout for. Usually this is the toughest part to find because this is just finding the value of the function, which we have. So finding g prime, need g prime of t. G prime of t is simple to find. G prime of t is the derivative of 25 plus 3 sine t, which is the derivative of this is 0, and the derivative of this is just 3 cos t. Okay, so that describes the change. This is similar to our temperature function, but a little bit different. You notice there's nothing on the inside here because we can't quite deal with that yet. But this would describe the rate of change of a simpler park, let's say, where it's goes through a cycle every 2 pi hours. But at any rate, this is our derivative. So g prime of pi over 4 is 3 cos pi over 4. And the cosine of pi over 4 is 1 over radical 2. So this is really 3 over radical 2. Now you can get a decimal approximation. That's fine. But I'm just kind of moving through this quickly. So now we go back to our equation of the tangent line, the line that will approximate this function. Y minus g of pi over 4. We've got this for g prime. G of pi over 4 is 25 plus 3 sine of pi over 4. Sine of pi over 4 is also 1 over radical 2. It's 45 degrees, so sine and cosine are equal. So 3 over radical 2. So we have this. Again, you are welcome to get a decimal approximation here. I'm just going to keep it in exact form. T minus pi over 4. So here, even though it looks a little weird with all of the radicals and pi's and whatnot, this is an equation of a line. Y minus a equals, y minus g of a equals g prime of a times t minus a. And so what you can use this to do is approximate values a little bit after this point and a little bit before this point. Okay, and there are some problems where we do that. It's called the tangent line approximation, and we have a whole section devoted to this coming up. But I wanted to kind of give a little bit of a applied problem and in the midst of these kind of just grinding out derivatives. All right. So that's the set of problems I wanted to do to set you up for your homework. And the last video I'll do is just some brief insights into sine and cosine and some things that I think will help you understand this more deeply, and again, need less time looking things up and recalling things when working through actual problems.